Okay, so we now know that the posterior estimate is equal to the prior plus the weighted version of the innovation. You can rewrite, you can see this is a linear combination. So X minus is weighted by this matrix, Z is weighted by this matrix. Are you with me? You can rewrite this way, both refer to the same thing, but it is in this fashion I'm going to be able to make the Kalman filter work. So what did I do? I used the dynamics to make the prediction. So this is the prediction of today coming from yesterday. Today's observation come. I difference today's observation from the model counterpart from yesterday's and add it to that and then repeat the show. That's Kalman filter essentially. But I'm not done because I need to tell you how to determine K. I did not tell you how to determine K. K plays the role of A. A was decided by minimizing the variance. K is going to be decided by minimizing not the covariance, but the total variance. You cannot minimize covariance. Let's talk about that for a moment. Why? Covariance is a matrix. You can't minimize a vector. You can't minimize the matrix. We only know, we do know many things, but we don't know how to minimize a vector. We don't know how to minimize a matrix. We need a scalar measure of a vector. We need a scalar measure of a matrix. Are you all with me, please? You need to know what is that we cannot do. What is that we could do. So I need to be able to convert the information of a matrix to a scalar. The total variance is the trace of the covariance matrix. So find K such that the trace of the covariance of X plus is a minimum. From now on, statistics, algebra, minimization takes over. There is no methodology, there is no nothing. It's simply quite mathematical. You need to be able to very patiently bulldoze through the arithmetic. So how do I compute the total variance of that? I'm sorry. This is where we are. Now, I have to go to the blackboard, so I will stay here. Can I stay here? Oh, please. Okay, good. Now, let me, E of X transpose X is a matrix. Well, I'll wait on that. I'll wait on that first. Maybe I'll go. Now, look at this now. If I put the transpose in here, it becomes an inner product because that's a transpose of vector times the vector. If I put the transpose on this, it becomes a matrix. Everybody? That's why I wanted to write. So let me first talk about that now. So expected value of X transpose, that's a covariance matrix. Expected value of X transpose X, that's the inner product. Expected value of the inner product. So the expected value of this, so this is a scalar. The trace of a scalar is itself. Everybody please. Mathematicians are troublemakers. You have to make trouble to be able to find the truth. You remember, I represented X is equal to A times X plus 1 minus A times X. I added and subtracted. Adding, subtracting, cancelling, multiplying, these are all mathematical tricks. Why do you do these mathematical tricks? To extract the truth. So that's exactly what is done in here. So this is already a scalar. The trace of a scalar is itself. Expected value is an operator, trace is an operator. These two operators commute. So expected value of the trace is the trace of the expected value. And the trace, you also know, the trace of AB is trace of BA. So I am now have said that the total variance of X plus is the expected value of the trace of the covariance matrix, which is equal to the trace of sigma plus, where sigma plus is the covariance matrix of the posterior estimate. posterior estimate. I hope you're all with me now. So I need to be able to, so this is simply an expression. I want to be able to compute this expression. To that end, I want to go back to the actual expression x plus. Everybody, are you all with me now what I'm doing? I computed the expression. There are three terms: the prior, the quantity x, and the noise. So I'm trying to center this. Centering means subtracting the mean. So x plus minus x is equal to this quantity. Now look at this. This x plus minus x comes in here, comes in here. So I'm going to substitute this term in here, this term in here. So there are two terms, that will become four terms. Everybody? How many of you are with me? Very simple. It looks a little complicated. The complexity is not conceptual. We have done all the conceptual part. It is simply bulldozing the algebra. How many of you are with me? So if I substituted that, I'm going to get an expression for sigma plus. I substituted that, I very patiently multiplied the whole thing. There are too many terms, so what is that I do? I'm changing the variable. One of the terms, I'm going to call it d, and d comes in here. Now look at that, this expression now. With d being a transformed variable, sigma plus is equal to sigma minus plus k d k transpose minus k h sigma minus h transpose k. Who is the unknown? Unknown is k. And what is k? K is a matrix. So this term is a quadratic term in the matrix. This term is a linear term in the matrix. This term is a linear term in the matrix. Hey, this is our old friend. Are you with me, please? We saw it on Monday morning and the Monday afternoon first class when I was trying to teach the linear least square fit. Now the whole question is this: I have to be able to minimize. You have to choose k that minimizes the trace of that. The trace is a scalar. The trace is a function of the elements of the matrix. K is a m by n matrix. So it is a multivariate minimization. What is the total number of variables? N m. Are you with me? How many of you are with me now? Come on, guys. You have to understand the steps. Are you with me? Think of a civil engineer trying to create a building. What does he do first? Find a space. Decide on the square area. Get a design. And do the design. Then implement the design. So that preparatory work may take 6 months to a year. Then the work starts. Planning is everything. So that's the planning I'm talking about. Are you with me? Now what he's doing is the minimization. So preparing the material needed to be able to pose the minimization problem is the planning process. And that's what this slide talks about. Now I have to perform the minimization. Now look at this now. I know how to do the minimization with respect to a scalar. I know how to do a minimization with respect to a vector. Now I know to do a minimization with respect to a matrix. You all have an aha here? That's right. I want you to think about that. The colors of the problem fundamentally is minimization, but the specific challenge changes because what is that I'm minimizing with respect to? Scalar, vector, matrices. With me? So there are several ways of doing this. One is element by element. Another is column by column. Another is row by row. In our book, we talk about all the methods. Are you with me? It is very easy to understand the column by column minimization because I already know how to minimize with respect to columns. That means I'm going to fall back on my strength to be able to reuse the techniques I have already learned. Now, do you know why I prefer Blackboard? That's right. Are you all with me? That's why I did the whole thing in the Blackboard. If I did this thing in the morning, you will hate me for life. He said yes. He said yes, he did. Please don't hate me. Don't hate your teacher. Your teacher is the one who put up the light for you. Are you with me? I will make your job a lot more difficult, but your job is a lot easier. Why? The path has been cut. The trail is known. You simply need to be able to carry a heavy load while walking the trail. That's it. Okay? So choose K to minimize this. We solved a similar problem earlier. Now I'm going to give you the optimal value. Are you with me? I'm not going to show you the process of optimization. That detail is given in the previous part of the slide. Everybody? Are you all with me now? So I want you to believe me. Don't believe me. You got to go and check. You should believe your teacher. You should believe your mentor, but always check on him by doing it, verifying it. Sir, you said is right. Sir, I have a problem in what you said. Where is it coming from? That's the level of discussion you should have at this level of PhD. All of you? So if I solve this problem, I get a K. I'm sorry. I get a K. So the optimal K is given by this. I'm going to substitute for my D. So the Kalman gain is given by this. Now let's look at the structure of the Kalman gain. Sigma prior, H transpose. Now look at this matrix. This is a symmetric matrix. H sigma inverse H transpose, that's a symmetric matrix. This is partially definite, this is partially definite, inverse exists. So you have the burden to prove that this sum is non-singular. Are you with me? Those are all part of the folklore. Part of the folklore. Part of the folklore. So once you have this, I have the Kalman filter equation. What is that? The posterior is equal to the prior plus the Kalman gain times the innovation. All of you with me? Everybody please. How many of you are with me? But this is random. It is a covariance associated with it. The covariance of this is the covariance of the prior. I'm subtracting something. Subtracting something means I'm making it less. That means the posterior has less covariance than the prior. That's exactly what I told in here. You remember? The variance of the optimal estimate is less than the minimum of the variance of the two input quantities. I have reduced uncertainty. Data assimilation reduces uncertainty. Are you all with me? Hey, this is the crux of Kalman filter. So what is the only thing I need to do now? Where in the world? Sorry. I have to get my direction right. Good. And what is the covariance of this? It is given by this. And where do I get this covariance from? I already know the expression for the covariance. I computed K. You substitute K in here. Simplify. Now you can see that's a marathon matrix multiplication. Matrix simplification. That's a marathon matrix algebra. Please do, it won't hurt you. Are you with me? Matrix algebra never hurts you. Please do. I want you to check it. All of me? So what is it I got? I got the best estimate of today's weather by combining the prediction from yesterday and by combining it with today's observation. Not only I got the best estimate, I also know its covariance. I also know the covariance of the estimate of the present day weather is better than the covariance of the prior that went into deciding my posterior. You all have an aha? That's the reason we are talking about Kalman filter after 64 years. All of it, me? It is sequential, conceptually very simple, elegant. It has its own challenges. The challenges comes from the computational difficulty. I'm going to tell a quick story now. Kalman published he was working in this paper 58, 59, he submitted in 59, it was published in 60. Okay? At that time, the moon landing mission was at its peak. President Kennedy was the president of the United States. He has told the Congress, I'm going to put a man on the moon in 10 years. So NASA has taken this project. Everything is going on towards firing the rocket, going towards the moon to land a man on the moon. So what is one of the problems engineers found out? You design the rocket such that it follow a particular trajectory, the designed trajectory. But you fire. The actual trajectory need not be the design trajectory. If you don't follow the design trajectory, you will miss the moon. Are you with me? Even see, we are traveling hundreds of thousands of miles. A little change the angle. Are you with me? Will put you off the track. So what is that they wanted? They want to be able to do what's called a mid-course correction. They know very well, this is the design path. The actual path will be closer to the design path, will not be exactly equal to the design path. I need to keep this vehicle as close to the design path as possible. That means I need to be able to fire engines on the body of the aircraft to align it. Just like you align your car to follow the car. You have to fire the appropriate engines. So which one to correct? To be able to decide which one to correct, you need to know the error. The error between the actual position and the desired position. Desired position is the target. Actual position is the observed position. There is an error. How do you correct the error? At that time, Kalman was invited to present a seminar in one of the labs in California. Kalman presented the lecture. Engineers knew this is it. This is the God-given gift. So what did they do? They were working on an onboard computer, which is a 8-bit microprocessor. It's a very rudimentary microprocessor, 8 bits. Today's microprocessors are 32 bits. They wrote a program on the onboard computer to be able to monitor. So Kalman filter was implemented in the Apollo mission. So the aeronautics people, astronautics people were the first one to be able to get the benefit of Kalman filters. Almost all the early applications of Kalman filters were in astronautics. With me? So what that I want you to do, please do this. Applications of Kalman filter in moon landing mission. Please go there, download a couple of papers, read them. Those guys did it in 1960, middle 1960. It came into meteorology only in the mid-80s. So what is the difference? We don't use the Kalman filter today because the matrix computations are going to be very, very demanding. Let's talk about one thing at a time right now, just to tell you, look at this now. H is the m by n matrix. This is the n by n matrix. This is the n by n matrix. I got to do matrix multiplication. I have to add this matrix. I have to inverse it. It is everything against what I said. You remember? Never do matrix multiplication unless that is what you want. Never do the inverse unless what you want. But that's exactly what is needed here. So it's an elegant solution that demands a lot of computer time. So when you are talking about the state vector space in meteorology, n, million, it is not that I don't know how to do. I don't have the time to do it. Because I have to make the forecast every 24 hours. Such problems are called computationally infeasible. I know how to solve it, but I don't have enough resources to be able to make it practical. All of you? Everyone, please? That's right. So the posterior covariance computation in Kalman filter is the most demanding part, is one of the two most demanding parts of Kalman filter. Oh, I have already come to this. Okay, I'm going to give you a reference. Sage and Meltzer, Estimation Theory and Applications, is a very good book on control theory. It's a very delightful, enjoyable introduction to various aspects of estimation theory and application to Kalman filtering from an engineering perspective. Good. Now let me go to the other. Can you help me on that? Can you help me on that? I don't want to screw up the machine. I want to go to the Kalman filter chapter.
The next slide.
Yeah, next one. So I'm now going to complete the story. I'm given a linear stochastic dynamic system. Okay? I'm having linear observation which are corrupted by noise. So what is the model? The model can be linear or nonlinear. In the case of linear model, xk plus 1 is equal to m of xk plus wk plus 1, that is the model noise. This is the nonlinear function, that is the model noise. You may wonder, why model noise? Models are abstractions of reality. Reality is much more complex than your model can capture. Every model is an approximation to reality. So what is that you don't consider? In general, modelers try to capture what is called the large-scale phenomenon. The model captures large-scale phenomenon, but there are lots of small-scale phenomenon that the model may not capture. Small scale correspond to larger frequency. I hope you all should know that. White noise is an example of a very high frequency. So I'm going to model the observation noise by a high frequency white noise. Is that correct? Is that kosher? That's one starting point. In other words, I recognize my model has errors. I want to be able to compensate for the errors. If I know how to compute the error, I would have already included it into the model. I don't know it, so I pray to my good Lord and then say the unknown error can be modeled by a white noise. What is the property of white noise? White noise is temporally uncorrelated. Sometimes the error may be correlated. Correlated noise is called red noise. Uncorrelated noise is called white noise. You know the reason why. White color, when you pass through the prism, you get multiple colors. You can create filters using which I can create a red noise from a white noise. Electrical engineers do this every day. Are you all with me? Red noise, white noise, broadband noise. So noise comes in various shapes and forms. If it is not a white noise, the calculation becomes much more involved. Are you with me? So I want to make sure I have a beautiful theory by making some simplifying assumption, but without leaving the errors unanswered. So I'm answering the error by including some form to compensate. So if you don't like white noise, you can add something. The methodology is parallels this. All of you, always please learn, you need to be able to do it in one way. If you know how to do it in one way, then if the conditions do not hold good, then you know where to make the changes to accommodate the newer conditions. Are you with me? There are lots of derivations. There are probably a couple of dozens of books written on Kalman filters from engineering perspective, from applications perspective, from aerospace application, meteorological applications. Are you with me? Different books emphasize different types of errors, different types of model, different types of applications. Please see, it has been around for 60 plus years. There are at least a couple of dozens of books on this. Please go and Google books on Kalman filtering. You see, it'll fill pages after pages. Please do, please do. So, I'm going to consider the linear model. Why am I using WK? Then, if I correct the model error, then the model is closer to reality. Are you with me, please? So XK is the true state. That's the model error, which is white noise. X is a n vector, M is a matrix. Observations are noisy. Observation can be zk h of xk or matrix times xk vk. This is a nonlinear function. This is a linear matrix. I'm talking about both linear and nonlinear formulations simultaneously to be able to see quickly the differences between linear and nonlinear cases. Everybody, I'm assuming my noise. So look at this now. Vk is the observation noise. Wk is the model noise. Wk is temporally uncorrelated, is white. Vk is also temporally uncorrelated, is white. And Vk and Wk are uncorrelated among themselves. With me? So now you can consider several cases. What happens if Wk is not white? What happens if Vk is not white? What happens if Vk and Wk are correlated? During the 60s and 70s and 80s, every one of these problems have been solved as a PhD thesis. Are you with me? So this was a great source of problems for PhD. Are you with me? There are tons of PhDs come out of this, all around the world. All around the world. Do you see the richness of the problem, please? So we are going to make the simplest possible assumption. When you are breaking new grounds, you don't have to solve all problems. Kalman was breaking new grounds. So he said, I want to present the elegant principle using the simplest possible case. Extension, let others worry about it. He never looked back. He never worked on Kalman filtering again. He let others do. There are hundreds of people who made their living out of this, including me. Are you with me? That's right. Are you all with me? That's right. So you got the model, you got the observation. Now, what is filtering in Kalman filtering? How many of you know the answer to that? We know filter coffee. We know filter to get the sediments out of something. So filtering is something that stops the unwanted thing to pass through. That's a colloquial use of the word filtering. Filtering in mathematics has a very special connotation. That's what I want to talk about first. So there are three concepts: filtering, smoothing, and prediction. I don't know how many of you have heard, known. Norbert Wiener, I mentioned this in one of the classes. Kolmogorov. These are two of the greatest mathematicians of this century, maybe for all times. I'm not qualified to grade them, but they have done such a fundamental work. These are two of the greatest of the mathematicians. Kolmogorov was in Russia. Wiener is an American mathematician. In the 40s, they were working on similar problems. They independently came to similar conclusions. Both of them written books with a similar title, not knowing what others were doing. Are you with me? Homework problem. Norbert Wiener, please go and read his history in Google. Kolmogorov, please go to Google, read the history. Gauss, please read the history. Come on, guys, you have to have a sense of history. Who did what, when, why, how, and so on. All of you? It enriches you. So let f of subscript n be the collection of all the observations zi coming from 1 to n. So that is the base, observation base. Based on that, if I'm going to estimate a quantity at a time k less than n. So n is the present. I have collected observation from 1 to n. I was told I cannot move to the blackboard because it becomes blurry. That's why I'm talking instead of writing. I like to write, but I was told, be careful, don't move too much around. So n is the present. I'm sorry. I am screwing it up. Yeah. So from the start to the present, I have collected information. Based on this information, if I am going to make an estimate at time k is equal to n, that is x hat k, that's called the filtering problem. Computing today's weather based on all the past information. Computing yesterday's weather, given all the information up to the present. Computing the weather 10 days ago, given all the way up to today. That's called smoothing. Computing the state of xk when k is greater than n, that is day after tomorrow. That's prediction. So smoothing, filtering, prediction, mathematically speaking, they are one and the same problem. So the filtering in Kalman filtering is used in this sense of filtering. What is that? I have a collection of information up to today. Using all the information up to including I know today, I want to get the best estimate. Are you with me? And if I want to use that to be able to make a statement about tomorrow, that's a prediction problem. If I want to go back and revisit and estimate something in the past, that's called smoothing problem. So within this category, 4D war is a smoothing problem. Why? I am trying to estimate the initial condition based on the observation from the future. I'm trying to estimate, I am given x1 to z1 to zn. I have gone past. I'm trying to estimate the past state. So in this category, 4D war is a smoothing problem. Kalman filtering is a filtering problem. Why do I do Kalman filtering problem? I do filtering and prediction. What is filtering? The best estimate of today. Based on the best estimate today, I want to predict what is tomorrow. So Kalman filter equation, filtering step, prediction step, filtering step, prediction step. Now you know what is filtering. So the word filtering in Kalman filter is a very technical term, very subtle term, and that's a distinction. Please remember, Kalman stands on the shoulders of these giants. Are you with me? Norbert Wiener has written a book, Extrapolation, Interpolation, and Smoothing. Are you with me? Please look at the book on Wiener. It's one of the most magnificent contributions to estimation theory. At the same time, Kolmogorov also published a book with almost a similar title, with similar results. What is the difference? Kolmogorov worked in the time domain, but Wiener was an expert in Fourier series. He knew more Fourier series than Fourier himself. He was a world expert. He was a giant in Fourier series expansion. Are you with me? So anything that works in the Fourier domain is called frequency domain analysis. Anything you work in the time domain is called time domain analysis. So because of that natural affinity, the work of Wiener was in frequency domain, Fourier domain. The work of Kolmogorov was in time domain. And there's a bridge between the two. Are you with me? So two giants worked on a fundamental problem, gave different shades of solution, which later found to be very similar because of the bridge between time domain and frequency domain. Are you with me? History is beautiful, history is rich. And Kalman was standing on the shoulders of these giants to do what he did. With me? So now I'm going to define the Kalman filtering equation. X naught. How do you pick X naught? I'm going to pick X naught from a random distribution. Nobody gives you X naught, right? So in 4D war, what is it we did? I pulled an X naught out of the blue sky. I ran the model forward in time. Observations came. I computed the errors. I then found the sum of squared errors. Everybody? And then minimize by computing the gradient, which we did that. So there we pulled it out of the blue sky. Here Kalman gave a little bit more structure. You pull your initial condition as a sample from a normal distribution. My friend is going to talk about sampling in his talk. Are you with me? Which is the fundamental part of implementing ensemble filters, particle filters, and so on. So once X naught is known, WK is the model noise. WK is also normal. I can compute the trajectory by making, so I know MK, I can have realizations of WK, so I can compute the state. I have observations. So what are the conditions in here? I am assuming X naught, WK, VK are uncorrelated. Do you see the problems there now? If they are correlated, what is the thing? But don't worry, it hasn't been solved. Kalman filter provided opportunities for so many PhD dissertations. Unbelievable number of PhD dissertations. With me? That's right. So what is the idea again? Given the information at time k, find the best estimate of xk that minimizes the mean square error. That's exactly I saw in the previous slide. Are you with me? That's right. So I'm going to use the model to create the background. So model is used for prediction, model is for creating the background, observations come, I mix the observation with the model prediction to create a new state, and the cycle continues. Are you all with me now? Do you understand it conceptually? Please understand, the mathematics becomes meaningless until you understand conceptually, aha, I know a path. Are you with me? You will always have difficulty with mathematics. Don't worry, you are alone. Everybody has it. Are you with me? Am I helping you? How many of you are with me? That's right. That's right. That's right. Good. So can I use the blackboard now? Can I stop this, or maybe these are derivations. Maybe I can use this now. I think this is enough for me. So I want to go from k minus 1 to k. Are you with me? K minus 1 is yesterday, k is today. Yesterday I did everything to compute the best posterior and its covariance. So the posterior is given by a hat. The forecast is given by an F. In meteorological circles, the posterior is called analysis. The F is called background. Are you with me? Hey, if you are in a discipline, if you use the same terminology as others, then they will say you are copying, right? You need to change the terminology. That's it. It's the old wine in the new bottle. The label is different. The wine is not different. So what they call analysis here is posterior. Posterior terminology comes from Bayesian philosophy. Analysis, I don't know why and where, but meteorologists call it analysis. Prior is again Bayesian. Background is again meteorological. I'm not complaining. You simply need to be able to understand these terminologies. If you do, then you can cut through. You can talk to anybody. If you understand their language, then you can talk to them. So this is the best estimate of the state and its covariance at time t minus 1. I use this into the model. I forecast the state and its covariance. Observations come in. So at time k, I have this, I need to combine. I use the linear minimum variance estimation to get this. If I got this, I am in the same position as I was here. Continue. Are you all with me? In the case of 40-bar, what we did? I started model from arbitrary. I'm going to repeat it once more, just to be able to see the difference. I pulled x naught out of the blue sky. I ran the model. I computed the forecast difference. Forward, backward, adjoint, compute the gradient, minimize, going to the optimum. Then run the model from the optimum beyond n. What is beyond n becomes a forecast. So you address a smoothing problem and then your prediction problem. Here you address a filtering problem and then the prediction problem. Are you with me? Filter, predict, filter, predict, filter, predict. Kalman filter. You all have an aha? How many of you knew this earlier? How many of you know it now? You also know the associated mathematical challenges, right? That's right. I gave you a glimpse of the mathematics using a scalar. The mathematics is a little bit heavier in terms of matrices, but doable. After MSc in physics or mathematics, this problem should not be heavy to any one of you. Are you with me? Come on, guys. Here I do the analysis. Now I'm going to talk about, yeah, go ahead.
Many times you are discussing about 4D war. In one of the paper, I read that 4D
I thought he was complaining that you are talking about 40 war too many times.
No,
okay, go ahead.
I didn't hear about the tangent linear model. What is the role of tangent linear model related to 4D war? In one of the paper I read that.
That's right. Maybe if you give me a few minutes, I can tell you after I finish this. Today's theme is Kalman filter. But okay, I did not use the tangent linear system because I used the linear model, linear equation. I indirectly use the concept without explicitly using the tangent linear. But if you go to nonlinear 4D war, are you with me? Generally, the lingo of tangent linear system comes in. The tangent linear system in mathematics is called variational equation. Again, in mathematics, it's called variational equation. Meteorologists called it tangent linear because they wanted to sound different. No offense to any meteorology, please. Come on. Don't feel offended. So tangent linear system is a fancy term meteorologists coined to represent what's called variational equation in mathematics. What is a variational equation? A variational equation can be used to predict the propagation of errors through the model. Do a Google variational equation. Come on, guys, you got to do this. Write this down. In other words, what is the idea here? Where is the variational equation comes in? I'm starting with x naught, I have a solution. I perturb the initial condition by delta x naught. You run the model. The difference between the two is the induced perturbation. Are you with me, please? How do you compute the induced perturbation? That induced perturbation can be computed as a solution of the variational equation. So the variational equation is derived from the original model to be able to characterize the propagation of errors in the initial condition. I've given you a full answer without working the details, but you can do that. So look at variational equation. Google this. You can. I would prefer for you to go to Wikipedia. I would prefer you to go to the library first. If not, go to Wikipedia. Are you with me? You can also write to me. I will help you. Okay, now you remember. Okay, now let's talk about. So this is the best estimate yesterday. I'm assuming the model is varying in time. Why? Only for the added mathematical generality. If the model does not vary in time, there is no subscript for the model. So starting from the best estimate yesterday, by giving it to the model, I'm getting XF. So the forecast is essentially the solution of the model starting from the previous best estimate. And how do you compute the covariance? The covariance, to compute the covariance of the forecast, I need to compute the error of the forecast. If you compute the error, then the forecast covariance can be computed. This tells you how to compute the error and the covariance. And what is the forecast covariance? The forecast covariance at time k for the forecast xk is given by this. Model the previous posterior covariance, model transpose Q. This is a killer. This is the n by n matrix, this is the n by n matrix, this is n by n matrix, two matrix multiplication. How many of you know to multiply two n by n matrices, it takes n cube number of operations? If you know, raise your hands. Come on, guys. That's a simple problem in linear algebra. Homework problem. Please, you got to do this. You got to do this. What is the total amount of computation you have to perform to multiply two matrices? To multiply two matrices, you have to do addition and subtraction, addition and multiplication. Compute the total number of addition, compute the total number of multiplication, verify that functions grows as the cube, the third power of the size of the problem. So if n is a million, what is million cube? Million is 10 to the power of 6. 10 to the power of 18 is the number of operations. Are you with me? That's right. So it is not that I don't know how to do. There are two matrix multiplication. So this is a bottleneck, computationally, not conceptually. So computing the forecast covariance is an extremely demanding computational problem. Then I do the model predicted observation. I now come to the Kalman filter stage. So I have the forecast. So what was x minus now becomes x superscript f. What was x plus now becomes x hat. So this is the model predicted, the actual observation, Kalman filter, Kalman gain, innovation, prior. The Kalman gain is a complex matrix. It consists of several components. Are you with me? So this is the forecast equation. This is the observation equation. This is the model forecast. That is the equation that computes the posterior. All of it me? Come on, guys. So you use the model to get this from here. You use the model to get this from here. Once you got here, somebody else gives you these two. You combine the two to get here. Repeat the show. I'm talking about all properties now. What if this? What if this? What if this? What if this? What is this? What if this? Are you with me? All special cases. You got to sit tightly by yourself. Please make a good tall cup of hot coffee, couple of sharp pencils, good notebook, sit by yourself, concentrate a couple of hours every day. Nobody can touch you. You become a master. You need to hit it continuously. Are you with me? All properties. Good. Now I come here. Computation. So how much time does it take to compute the forecast? This is the matrix. That's a vector. Matrix vector multiply. Matrix vector multiply takes 2n square operation. How do you do matrix vector multiply? Row, column, inner product. An inner product takes how long? N multiplications, n additions. So to do inner product of two vectors, it takes 2n operation. To do a matrix vector multiplication, there are n inner products you need to do. So 2n times n is 2n square. So to compute the forecast covariance, it takes 4n cubed plus n square. To compute the Kalman gain, this matrix is this much time. To compute the inverse, take this much time. To compute the forecast covariance matrix, it takes this much time. I'm sorry, to compute the Kalman gain takes this much time. So the total time to compute the Kalman gain is this much. Now, what is that I would like you to think about? Somebody told me the following: n is a million and m is something else. I don't know whom I talked to. So in meteorological problem, n becoming larger and larger and larger. M, you are the one who talked about that, right? M becomes larger and larger and larger because you are putting more sensors. So M is large, n is large. computationally is a heck of a problem. Not that I don't know. I may not be able to store all my matrices in the fast memory. I may need to store parts of the data in secondary memory. If you put parts of the data in the secondary memory, you have to bring it in and out. Are you all with me, please? I don't think you can store a million by million matrix in any computer we have today. All of you? That's right. Then I need to compute the posterior forecast covariance. That takes this much time. And then I had to compute the xk plus 1. So I have itemized every part of the calculation. It is a sum of all is the total amount of time. Are you all with me, please? That's right. The first thesis on the application of Kalman filter to meteorology was done at the New York University by a person named Cohen, C-O-H-E-N. Are you with me? He went to work for NASA. He spent all of his life in NASA. He continued his work in that direction. So he was the first one to be able to bring in his PhD thesis into the meteorological world. He applied it for shallow water model. He discretized the shallow water model. He considered the discrete version of it, and he tries to apply. He succeeded, but he brought out the importance of amount of time and space needed and showed that for a truly large-scale problem, this line of approach may not be feasible. He didn't say it is not impossibility, it is infeasibility. These two are different. Impossible means you can't do. Infeasible means I don't have resources to do it. I have the knowledge, but I don't have the power. Are you with me? How many for me? That's right. I give a couple of examples. I don't think I want to go over that. So I'm doing a scalar model. You remember that? Xk plus 1 is 8 times xk plus 1 wk. I'm applying everything to a scalar model. I'm showing the complete filter equation. So look at that now. A is the model parameters. A can be in between 1 and infinity. A is equal to 1. You get various different kinds of models. I derive the complete filter. I compute the errors. I compute the forecast covariance. I'm considering the asymptotic behavior of this filter as a time k. N is for the state vector, m for the observation vector, k for time. All right, k tending to infinity. I give all the stability equations, analysis of variance, and this is the chapter 27 in our book. That is me. I don't want you to buy the book because it's very expensive, but what is the one thing I would like you to do? If you go back, you're all coming from different institutions, make sure your library buys it. Your library may not by itself do it. You need it if you are planning to work. So I don't know how many of you would like to work on data assimilation after the seminar. I hope you continue, right? How many of you, after hearing at least part of the seminar, still want to continue in data assimilation? That's a good number. You're all tough people. Good, wonderful. You need the toughness. World belongs to people who can withstand things. Are you with me, please? So what is the suggestion? Go back to your institution, ask your library to buy. I'm giving all the slides of the lectures through Dr. Govindan Kutty, and you should have access to all of them. With this, let me stop. I still have some time. I would like to spend that time in some question answering. Are you with me? Govind, is it okay?
Yeah, it's fine.
Good. You can probably ask him to stop this so that I can go to the board. I can be a little freer to move around. Yeah, I can stop this. Please remember, I also have given you a set of some 50 problems related to data assimilation through Dr. Govindan Kutty. You should all get it. I want each of you to be able to solve it. What is that I would do if I were you? I'll buy a notebook only on problems. I'll have another notebook only on Kalman filter. I'll have another notebook only on 40-var. I have another notebook only on Bayesian. Are you with me? Come on, guys. Partition it. Work it out. You become a master. There's no doubt about that. You will become. Good. My friend is not going to leave me until I do mathematically what this tangent linear model is. So I'm going to talk about tangent linear model unless you have other questions. But think about it if you have other questions. So I will quickly talk about the tangent linear model for a few minutes. I think that's a good question. One second. I'm doing this work. I'm not hearing you. What do you say?
And if it is possible to discuss once again control variable, control vector.
Oh, good. He and I talked about it during breakfast, but I'll do that now. Suppose I have a model, xk plus 1 is equal to m of xk. Is a nonlinear model. All with me? So x1 is equal to m of x naught. Are you with me? So if I started at x naught, I have x naught, x1, x2, x3, xk. Now I'm going to perturb it. This is x naught plus delta x naught. So to start with, I'm going to call it bar. X bar naught is an initial condition. I'm going to get a bar. Now I'm going to define an x naught, which is equal to x bar naught plus delta x naught. So this is going to be my x naught. So I'm going to get x1, I'm going to get x2, I'm going to get x3, I'm going to get xk. So in the problems of meteorology, they call this base state or base trajectory. Why base? Why not? Don't worry too much about these nomenclature. You need to understand what the object is. Knowing that different areas call it by different names. So this is delta x naught. So this is delta x1. This is delta xk. So the whole question is, how do you compute delta xk as a function of k? In other words, I want to be able to compute this time series, delta x1, delta x2, delta x3, delta xk. Are you with me? And what does this time series tells you? It is the propagation of the initial perturbation. All of you? What is one way to do it? You run the model once, you run the model second time, look at the differences. That will give you the actual difference. But I can approximate it very cleverly. All of you with me? How do I approximate? The approximation comes as follows. So x1 is equal to m of x naught. X naught is equal to x naught bar plus delta x naught. Are you all with me, please? I'm going to expand this in the Fourier series expansion, in the Taylor series expansion. How many of you have heard of Taylor series? How many of you know Taylor series? So what is the Taylor series for this? M of x bar naught plus delta x naught is equal to m of x naught bar plus the correction. And what is that correction? That's called the Jacobian of m at x naught times delta x naught. And what is this? This is the n by n matrix. And what is the Jacobian? dm at x naught is equal to partial of m I partial of m xj evaluated at x is equal to x naught. And that's the matrix. That's the n by n matrix. And that is called, this in mathematics, this is called Jacobian. You remember gradient? You remember Hessian? Add one more to it, Jacobian. Are you all with me, please? So to a first order, I can approximate this value by this. Therefore, this is equal to m of plus dm x naught delta x naught. I already know x1 bar is equal to m of x bar. Call it 1, call it 2. If you do 2 minus 1, that gives rise to delta x1 approximately equal to x1 minus x1 bar, which is equal to m of x naught bar plus dm x naught delta x naught minus m of x naught bar. Are you all with me? So these two get cancelled. Therefore, delta x1 is equal to dm x naught times delta x naught. So generalizing this, delta x2, which is equal to dm x1 bar times delta x naught. I should say this should be bar here. I missed the bar. So it is Jacobian calculated with respect to the base trajectory. Are you with me? Everybody with me, please? So what did I get generally? Delta xk is equal to dm delta xk plus 1. That's a better way to say it. Delta xk plus 1 is equal to dm at xk bar times delta xk. Are you all with me? Hey, this is a linear equation. This is a nonlinear equation. This linear equation talks about the propagation of error through the nonlinear equation. So this linear equation is called the variational equation for the original system. In meteorology, they call it tangent linear system. Not necessarily. That's not the way to do it. The variational equations are meant to compute the propagation of perturbations. It turns out that the errors, when they propagate through a nonlinear system, to a first order accuracy, I can compute them by using a linear variational equation. Are you with me? That's right. The second question he asked this morning, and he wanted me to tell for the benefit of the entire class, is the following. Why do we call, or what do we call as control in data assimilation? So let us take a discrete model, m of xk alpha. I'm trying to include an explicit set of parameters. Alpha is a parameter. Every model must have some parameter, right? So the solution for this xk can be written as a function of k, as a function of x naught, as a function of alpha. The solution depends continuously on the initial condition. The solution depends continuously on the parameter. So if you change the initial condition, solution changes. If you change the parameter, the solution changes. So what is the problem in data assimilation? There is a set of observation given to me. There is a model trajectory. My job is to move the model trajectory as close to the observation as possible. If I want to move the trajectory as far close to the observation as possible, I need to have a control. When you're driving, if you want to turn left, you need a control. Turn right, front, backward. The steering gives you the control to make the car do what you want to do. Here, what is it I want to do? I want to move the entire solution of the differential equation towards the observation. To fit the observation in what sense? The least square sense. So I want to be able to have a control to make this move possible. How do we make this move possible? By changing the initial condition, by changing the parameters. Therefore, the collection C of x naught alpha in the meteorological context is called the control. And this is not the only way control. In engineering, control comes another way. You are driving a car, what is the control? Your pedal. Are you with me? The thrust you give. That's called external control. So in the car, there are two types of control. The thrust you give, that's one control. The steering angle is the second control. You use these two controls intelligently to get from point A to point B. Are you with me? In data assimilation, I want to move the trajectory from one place to another place. I'm not allowed to use external control. So there is no throttle, there is no gasoline. I have to use it only by changing the initial condition and parameters. Now, do you see there are two forms of control? One is an external forcing. That's one kind of control. I control the temperature in the room. Isn't that what you say? That's right. The air conditioning control. That's an external control. So this is a kind of an internal control, but you don't say internal control, external control. Once you know the difference, you know what it is. Any other question? Is there anything else you thought, one second, is there anything else you thought you wanted to hear but you didn't hear? You still have one more week. My friend is coming next. You can pose the question to him too. I want you to think about, you have to generate good questions. You need to keep thinking about these problems. Are you with me? That's the key. Yeah, yes ma'am.
Sir, I want
louder.
I want to ask you about the white noise and red noise you talked about.
You have to talk a little louder. I'm an old man. I'm losing good part of my hearing, so I want to be little slow and little louder.
Okay, so I want to ask you about, you said about white noise and red noise. How we can identify them graphically? If, like in plots, we can say that this is white noise or this is red noise.
White noise or this noise, we cannot do it by graphically. You have to compute. You know how to compute the correlation for a time series? Yes or no?
Correlation.
Okay. I have a time series. There are properties of time series. Stationary time series, non-stationary time series. A non-stationary time series means the probabilistic rules that govern the evolution of the time series itself is varying in time. Climate is a non-stationary process because much of it we believe happened during the past 50 years. We have been burning carbon. Are you with me, please? So the regime that we are in is not the same regime 100 years ago. The regime has changed. So climate analysis becomes very difficult because of this non-stationarity. Non-stationarity is something that is changing. While it is very difficult to talk about a stationary object, it is more difficult to talk about the thing that is moving. Are you with me? So the first assumption you have to make, it is stationary. Okay. And the stationarity means strong stationarity, weak stationarity. I'm not trying to tell you things to impress you, but I want to tell you basic things. So how do you test for stationarity? So if you have a long sequence, you split it into two, compute the average of the first half, compute the average of the second half. If they are not too different from each other, you can say the expected value doesn't change. You compute the variance of this, compute the variance of this. If they are not too different from each other, I can assume the variance is not too different. Understand me? So you need to be able to ensure that it has inherited the property of near stationarity. Once you have guaranteed it has inherited the near stationarity, then what is that you need to do? You need to do what's called autocorrelation. Are you with me now? Autocorrelation is a function of the separation. Autocorrelation between t and t plus k. Autocorrelation is called rho k. If the autocorrelation, if you consider k is 0, the autocorrelation is 1. If for k greater than 1, if the autocorrelations are very small, ideally it has to be 0. If it is very small, then you can say for all practical purposes, they are uncorrelated. That means the temporal correlation is close to being 0. One of the necessary conditions for the definition of the white noise is that the temporal correlation must vanish. Are you with me now? That's right. That's all. You refer to books on time series analysis or go to Wikipedia. How to compute, how to test a given time series, is a white noise or not. There is somebody who did a project on time series from, that's right, talk to her. She knows that very well. She knows that very well. I want to give you one more information. My email is at ou.edu. All are lowercase. If you think I have a question, if I can be of help, you can write to me. I'm going to be on travel for a couple of months. But so if you send me an email tomorrow morning and if I didn't reply to you, don't feel bad. I will try to reply to you soon enough. But if I know it, I will share it with you. All of it, me? That's right. Somebody asked me, how bold are you to tell that you can write, or you can ask everybody to write? I tell you, the percentage of people who write to me is very small. But people do write. People do write. And those who care to write, I always converse with them. I always help them. Are you with me? All of you? This man is not going to let us out of this hall until it's 10 more minutes. He's the gatekeeper. Any other question? Come on, guys. Okay, so what's that my friend is going to do this afternoon, starting this afternoon? He's going to pick up from where I left. I showed you Kalman filter is a beautiful idea, but it's an expensive idea. Everybody likes to have a Rolls Royce, but not everybody can own it. So what we end up doing? A Maruti or a two-wheeler. So when going gets tough, I have to do my job, but get around it in a cheaper way. Ensemble methodology, ensemble realization of this filter is a meaningful, cheaper, computationally feasible way to do the business. Are you with me? So he is going to pick up from where I left. So he is going to give solution to address the computational challenges. Are you with me? All the lectures have very good connections. Dr. Vinith's lecture on Bayesian, we picked up on that. Are you with me? He is going to pick up on the computational complexity. So he is going to tell you how to do Kalman filtering without becoming a victim of the computational demands. Are you with me? That's ensemble filtering. particle filtering. All of you? Particle filtering. And then particle filtering is another version, and that is going to require lots of tools from sampling techniques, which are intrinsically statistical in nature. He's going to introduce you to advanced principles in sampling. So that's going to be a good continuity in form of theory. So by the time he finishes, you should know a good part of the theory of dynamic data assimilation. Next week, you will get to see a lot of graphs, because they are all going to talk about applications that will complement what we talked about in real world. And they will tell you examples of their work. All of you? Any other observation, comments? I hope you all enjoyed as much as I did. You know where I'm hiding? If you need help, if you wrote to me, you will hear sooner or later. More often than not, sooner. Okay? Wish you all the best. Keep in touch. Thank you all.
Do you have any more questions? If not, let us thank Professor Varahan for his excellent lecture for the last 4 days.
Thank you.
He was enlightening us with all the basic fundamentals of data assimilation. So you are truly an inspiration, sir, a teacher like me also. Thank you so much.
Now you know why I'm friends with him. Thank you, sir.
Thank you.
Thanks for the opportunity.
You accepted my invitation and came all the way over. I'm very thankful for you.
It's always a pleasure.
Thank you.
Hey, Bangalore is the place where I became what I am. I owe all of my thing to the education I received in the Indian Institute of Science. So I consider Bangalore as my second home. Anytime you call me, buddy, I'll come. But make sure you pay the ticket.
Thank you.